Welcome to the R video tutorial on the central limit theorem in R. This is actually part 2. If you haven't watched part 1, you might want to jump back to it. This is part of Statistics 321 at Virginia Commonwealth University, but anybody can use it. Okay, so if you remember from part 1, what we set up was a simulation to simulate the central limit theorem. And what we were changing was our sample size. So nsamp here is our sample size. nsim is the number of times we're going to conduct an experiment where we're going to draw from a population. We've created a container because we're going to use a for loop. This for loop is going to run through the simulations or experiments however many times we've said. So it's going to go start at 1, it's going to end at the number of simulations that we prescribed. In our last video, what we did is we pulled from a normal distribution and we saw the behavior. And a normal distribution is kind of nice. It's symmetric. We know the properties of it. Everybody's familiar with it. You've read it off of tables in your previous classes. So what we're going to do now is we're going to switch this to a different distribution. So let's suppose we have a gamma distribution. So I'm going to have a gamma distribution. I'm going to pull the number of samples. And let's say I want something along the lines of, let's say, 50 and 10. This should have a mean of 5 if you remember from a previous video. Here I'm going to change the x limits a little bit up to maybe 15, see how our picture looks. So we're going to take this. Remember, if you haven't watched a previous video, you can type all of this in, or you can hit pause and type all of this in. So we're going to run this and see what our data looks like. Okay, so maybe we don't need it to go all the way out to 15 here. So I'm going to change that up. So 10 was enough. And we're going to run at this and see what this thing looks like. So this is centered at 5. Maybe we want to play with it a little bit more. How about if we did 5 and 1? To really change it up. And what I'm trying to do here is give you a feel for what we can do with these distributions. Okay, now we need to have it go back out to 15, but we're getting a much better, fatter picture here. So let's have this go out to 15, and we'll run this just to see what we get. And this is what we end up with. Okay, so we have a distribution that is definitely right skewed, is only positive number, and this is not a normal distribution. How do we know it's not a normal distribution? Because we pulled from a gamma distribution, and a gamma distribution is not a normal distribution, so we know it's not normal. Okay, so let's do what we were doing last time, which is increase the sample size. So let's change this, go to 2, see what happens, and run the whole thing. Here we go. And notice it did shrink in a little bit. It's still centered around 5, which is what we know it's going to be centered at. Let's see what happens if we go to 5. Give this a run. Still a little bit right skewed, still centered at 5, but notice it's shrinking in massively like our other one did before. That's part of what the central limit theorem says. It says that this distribution is going to get narrower. And sure enough, it is. So let's go to 10. Let's see what happens at 10. And we'll give this a run. Look at the picture. And notice it's still centered at 5. It is a little bit right skewed, but it's starting to look symmetric. When we started off, it was highly right skewed, and now the histogram of the mean, so the data is right skewed, the mean is becoming symmetric. It's still centered at the mean of the population, which we know is 5 because we've created it that way, and the variance keeps shrinking. Okay, and this is what the central limit theorem says. I'm going to keep repeating it, and that's why I'm actually running many videos on this, is to emphasize how important the central limit theorem is. It holds most of statistics together, so understanding how it works is important. All right, so look at this. This is getting more symmetric. It's shrunk in a lot, and this tells us which values of a mean would be likely or unlikely from this population if we took a sample of size 20. So I have a population that has a mean of 5. Okay, likely would it be that if I took a sample of size 20, like I did here, that I would see at a sample mean of 10. And if you look out here, it's like, oh, it's extremely unlikely. And probably a sample mean of 1 is extremely unlikely. And that's what we're going to use to our advantage when we're trying to make inferences, because we're going to try to guess at what a population mean is, and understanding how the sample mean behaves will help us understand how to use this to create confidence intervals and hypothesis tests. All right, so we've changed this from a symmetric distribution, which was the normal distribution, to a gamma distribution, which is right skewed. And if I go back, we're just going to look at these real quick, just for comparison. Here was what the data looks like, the population, right skewed, centered around 5. But if I take a sample size of 20, the sample mean, not the data, the sample means look like this. They're relatively symmetric, they're shrinking in, and this is the idea of the central limit theorem. Okay, so we're going to jump to the next video where we're going to play with a distribution that's discrete, because the normal distribution is a continuous distribution, the gamma distribution is a continuous distribution. What happens when we jump to a distribution that has gaps in it, like the Poisson? It only allows whole numbers. So I'll see you in the next video.